Okay, Chapter 3, Section 4. This is called linear programming. Linear programming is a technique used so that businesses could either maximize or minimize their profits. There's other applications, but we're going to see that this is the way that we're taking this for right now anyway. So vocabulary first. What is linear programming? It's a technique that identifies the minimum and maximum value of some quantity. You will have an objective function, and that is the equation you build. So the objective function is the equation. Everything else is going to be an inequality. So this one will have the equal sign. Constraints are the limits on the variables. So if you can have no more than, well, that's a limit on some variable. So limits on the variables. And the feasible region is the shaded region that satisfies all inequalities. Shaded region that satisfies or makes true all inequalities. All right, that's called the feasible region. So in other words, if you were building things and selling things, the feasible region is the area that can come true. Okay, that's what's feasible. So what are our steps to doing linear programming? Well, the be-all end-all here is we are going to be graphing inequalities. The thing that you might not be used to as we go on with this is actually writing the inequalities that represent the conditions that are represented in the application problem. The first example gives us everything. And then you will see when we do the second example, we have to come up with the equations. So we have to write linear inequalities that demonstrate the situation. You will then graph the inequalities that you're already used to doing. The shaded region that they share is called the feasible region. That's your possibilities of what you can do. We're going to find the vertices and identify their ordered pairs, which could possibly be the intersection points of lines. You then have to find your max or min value by substituting the vertices, or those ordered pairs, into the objective function. All right, so for example, we're going to maximize this objective function. C equals x plus y. C typically means cost. All right, given these constraints, and here is the system. So for the first one, we're going to solve it for y so we can easily graph it. So we get 2y is less than or equal to 3x plus 6. Always make sure that you're putting the x in the front so that this is set up to look like y equals mx plus b. we're going to divide by 2. So we get y is less than or equal to 3/2 x plus 3. This is going to be one of our boundary lines. Excuse me. The second one, we solve for y. We get y is less than or equal to negative 3x plus 3. And of course, this is, we'll just put a box around it because we do have to graph that one as well. Now remember, anything greater, y being greater than or equal to 0, it means we're going to shade above, okay? This is a horizontal line. And the y values that are greater than or equal to 0 are going to be the ones above the 0, not below. All right, so before I graph these, I have to draw my axes on my coordinate plane. This one's the y. This one is the x. And my scale is by ones for both x and y. All right. Let's first graph this inequality. Y-intercept is 3, slope is 3/2. So I'm going to come to my graph. Y-intercept is 3. Slope is up 3 to the right 2, or down 3, left 2. I'm going to draw my line. I know it has to be solid because it's equal to. There is my first line. I'm going to test 0, 0 because it's up for grabs with respect to that line. Test 0, 0. Remember, you always substitute it into the original, which is way back up here. So negative 3 times 0 plus 2 times 0, that all equals 0. So my output there is 0 is less than or equal to 6. That's true. So since that's true, with respect to this blue line, I'm going to shade this way. I like to put the little arrows there so I don't booger up my whole graph. Now I'm going to do the next one in a different color. All right. I'm going to graph this line, and it is a solid line because of the equal to. Has the same y-intercept, 3, but the slope is negative 3. So down 3 to the right 1. Or up 3 to the left 1. And I'm going to draw that line. Again, I'm going to test 0, 0. Because the green line is not passing through 0, 0. The left side would be 0, right? 3 times 0 plus 0, less than or equal to 3. So 0 less than or equal to 3. That is also true. So I'm shading this way. And my last line is that y equals 0, right? There is a 0 slope. That would be 0x plus 0. So that's this line right on the x-axis. Oops, I kind of went uphill over there. Now, technically, I can't test 0, 0 because it passes right through 0, 0. you know, you could, unless you already know, y values greater than 0 would be above, you could test 1, 1. And you put a 1 in for y. Is 1 greater than or equal to 0? Yeah, that's true. So we're shading up. So my shaded section for this problem is inside that triangle. So now I'm going to shade the whole thing in. And that's called my feasible region. So if I want to maximize this objective function, or at least have something that will work, it's only going to work with any ordered pair that's inside the shaded region. But to maximize, you do have to substitute the vertices into the objective function, which was given to us, c equals x plus y. So I'm going to label these points A, B, and C, and off to the side, I'm going to say point A has coordinates 0, 3. Point B has coordinates -2, 0. And point C has coordinates 1, 0. Now I have to take these and I have to substitute them into the objective function. Okay, and the objective function is that c equals x plus y. So c equals, well, x is 0, y is 3. That's 0 plus 3. So my output there is 3. Again, c equals -2 plus 0. So c is -2. c equals x plus y again. 1 plus 0. And I see my value of c is 1 here. Since 3 is the biggest out of all of them, this is the maximum value of the function. So I don't think the process is difficult. It's just a lot of stuff. However, you have a lot of these skills already. You know how to put them in y equals form. You know how to graph them. You know how to do the test to figure out what the shading is. The last part is what you're going to have to remember to do, is to substitute the coordinates of your vertices into the objective function. So if you have any questions, you know what to do. Post on the homework discussion or ask in class. And we are going to take a look at example 2, which is on side 2 of the notes. Please make sure you're printing out the notes and doing the notes. It's not going to be good for you if you do not have the notes. Number one, you use the notes to assist you with your homework. And number two, I could give you a notebook test, and if you don't have notes, that's probably not going to be good for you. All right, side 2. Example. Here's an application problem. Now we're going to have to put everything together. They're not going to give us everything. A furniture manufacturer can make from 30 to 60 tables a day and from 40 to 100 chairs a day. It can make at most 120 units in one day. The profit on a table is $150, and the profit on a chair is $65. How many tables and chairs should they make per day to maximize the profit? Well, you're going to have to build some inequalities and your objective function. I'm going to say tables is X and chairs is y. You know, when you see words like is, or your verb words, okay, like spends or costs, that kind of stuff, that's where you're going to put your equal sign. So let's see. The profit on a table is, that's going to be my objective function. When you see phrases like, they can make from this to this, or from this to this, or make at most, that's a less than or equal to. That's your inequality look fors. All right, so it's saying a furniture company can make from 30 to 60. Doesn't that mean between 30 and 60? At least 30, but no more than 60? And we used X for tables, right? So X is going to be between 30 and 60. So my first inequality, I'm going to put the 30 there. Less than or equal to X, less than or equal to 60. Okay, so the tables is between 30 and 60. It can make, and from 40 to 100 chairs, I let the chairs be Y. So chairs is going to be between 40 and 100. So very similarly, Y is going to be between 40 and 100. All right. Profit on a table is 150. We're not there yet. It can make at most 120 units in one day. Well, aren't we talking about tables and chairs? So tables and chairs together can't be more than 120 units. So tables and chairs together has to be less than or equal to 120, because we can't make more than that. We can make less, but not more. So far, this is what our system is looking like. Let's get the profit, the objective function. The profit on a chair is $65. The profit on a table is $150. So the profit for my objective function is going to equal, table is my X, so that's 150 per table plus $65 per chair. Now, because the top two inequalities in my system are compound inequalities, we have to break them apart. Okay, so if I cover this part up and I read this backwards, this says X is greater than or equal to 30. And this side says X is less than or equal to 60. So I'm going to break those apart. X is less than or equal to 60. X is greater than or equal to 30. You've got to do the same thing for Y. Y is less than or equal to 100. Y is greater than or equal to 40. And then, of course, we have our last inequality, X plus Y is less than or equal to 120. So this is actually the system we have to graph. We've got the compound inequalities from the conditions that were given to us in the problem, but we had to break them apart so we can graph each one separately. Now, because I'm not interested in anything that's happening on the negative side of things, meaning quadrants 2, 3, and 4, I'm going to put my axes on my grid, which is up here in the top right hand corner. I'm going to put my axes on the far left and on the bottom. This is X. This is y. And I'm actually, well, we can extend this if you want, to indicate that the coordinate plane goes on. This corner here is 0, 0, and I'm actually going to scale my grid by 10. So I'm going to show that this one is 10, that's 20, so that's 30, 40, 50, 60, 70, 80, 90, 100, 110. Right, I do have to go that far because look at my numbers that I have here. I have 60, I have 100, I have 40. Okay, so I'm going to go by tens. Here I have 120. Okay, that's going to be my y-intercept when I convert that. And so that's 110, that's 120, and that's 130. So I have to go by tens. And I'm going to go by tens on the x-axis as well. 10, that's 20, that's 30, 40, 50, 60, 70, 80, 90, 100, 110. That should be good. Okay, so understand you have to scale your grid for these problems. All right, now let's graph x is 60. Remember, an x equals goes this way. So I'm going to look for where x is 60. That's on this line. And that's a vertical line. I can test 0, 0, right? So if I'm testing 0, 0, I would be shading left. Yeah, because that would be a true statement. 0 is less than. So I'm going to say with respect to this line, I'm shading to the left. All right, hopefully I have enough colors. The next one, x is greater than, well, I'll do the x's both in green. X is greater than or equal to 30. That would be another vertical line, rather. And I'm going to test 0, 0. Is 0 greater than 30? And, you know, I'm going back here into my system. Okay. First one was 0 is less than or equal to 60. That was true, so I shaded left. This one, x is greater than or equal to 30. Well, I have to shade to the right there because 0 is not bigger, nor is it equal to 30. So for this line, I'm shading to the right to get my feasible region. Okay, back to this. Sorry I had an interruption. Had to pause the video. So again, we graphed these two lines and we did the test, right? Testing 0, 0 to see which side to shade. With respect to this line, we shade left. With respect to this line, we shade right. Now I'm going to graph the y's. The y's are the horizontal lines. So I've got a y at 100 and a y at 40. So I'm going to draw my lines over here, cross at 100. Make sure you're looking at the right value. Oops. And at, what was the other one? 40. So that's 30, and between 30 and 50 is 40. All right. Now, let's test the 0 to see where we're shading there. All right, so with respect to this one, is 0 less than 100? Yes, so we're going to shade below that line. So this line, we're going to shade below it. And for the other one, y is greater than or equal to 40. Is 0 greater than or equal to 40? No, so we're not going to shade down, right, because 0 is down below this orange line. We're going to shade up. Okay, so far it's looking like we are shading inside that rectangle, but we have one more line to draw, and that's the bottom one. It's not in y equals form, so we have to convert it. So this is y is less than or equal to negative x plus 120. Okay, so 120 is my y-intercept. I'm going to put a dot up here at 120. Here's 110, here's 120. And my slope is -1, so I'm going to go down one to the right one. And really, I'm falling 10 and running 10, okay? That's why it's best to keep your axes the same. You know, if you go by 10s on one and by 5s on the other, then your line is going to look a little bit different. So if I fall 10 and run 10, 10 over 10 is 1. So this is -1. And I'm going to do that again, and again, and again. And just put a bunch of dots on my coordinate plane here so that I could draw a nice straight line. Now I'm going to draw this line. I could angle my measuring device properly. And now I have to test 0, 0, because with respect to the red line, 0, 0 is on the left. So let's test 0, 0. And remember, we're testing it in the original over here. The left side would be 0. Is 0 less than or equal to 120? Well, sure, it is less than it. So I am shading this way. Now, if I look at all the shading parts, my final feasible region is this region inside this, what appears to be a trapezoid. Right? A trapezoid has two parallel sides. If I turn it sideways, you can see the trapezoid right here. Okay, what's the next step? I have to identify my vertices. Here's vertex A. I'm going to go clockwise. That's B. This point is C. And this point is D. Right? I need the vertices of that trapezoid. And now I have to substitute my ordered pairs into the objective function. So are these problems hard? I don't say they're hard. You might have a little bit of difficulty converting the English to math. You shouldn't have difficulty finding the max or the min. That's just substitution. Now, are the problems long? Yes, they're long, just like this video. But, you know, there's not much I could do about it. We'd be doing this in class anyway. So I'm trying to find the max. All right, I've got 4 points, A, B, C, and D. I'm going to identify the coordinates of point A. Well, point A has coordinates 30, 90. Point B has coordinates 60, 60. Point C has coordinates 60, 40. And point D has coordinates 30, 40. Now it's going to be important that you know which ones are the X's and which ones are the Y's. You know, double check them up here. All right, what do I do with them? Well, I substitute them into the profit objective function. You could write the objective function right here, P equals 150x plus 65y, so that you're writing it only one time and not 4 times. So I have to substitute. This is 150 times x is 30 plus 65 times y is 90. 150, I'm going to write them all because they are the same. Space for x plus 65, space for y. Now I'm going to take the values for my ordered pairs and substitute them. I got 60, 60, 60, 40, and 30, 40. Now you need a calculator. So P here, you know, just type it on the calculator. Do 150 times 30. Actually, do it like this. Parenthesis 150 times 30, close it, add parenthesis 65 times 90, and we get 10,350. So that's $10,350. Okay, we're going to do the same thing for all of the other ones. And when you do this on the calculator, I'm not going to try to take up video time to show you calculator stuff. This one is $12,900. This max profit is $11,600. And this one is $7,100. Now, where's my max? Where's the most money I can get? Well, right here. This is my max. Now, I still didn't answer the question. It says, how many tables and chairs should they make per day to maximize the profit? And how much is that maximum profit? We already found out how much. Now, we have to take the coordinates for the ordered pairs, 60, 60, and write in a sentence, they should make. This one's nice because I don't have to differentiate. In other words, if it was like 30, 40, well, 30 is tables, 40 is chairs. 60 is tables, 40 is chairs. This one, 60, 60, they're both the same. 60 tables and 60 chairs. They should make 60 tables and 60 chairs per day for a maximum profit of $12,900. Okay, and this would be my final answer. In sentence form, I have answered the question. So, you might need a little practice converting your English to math to come up with your inequalities and your objective function, whether that's profit or whether that's cost. The rest of it, I don't think it's too tough for you to break apart the compound inequalities to get this system. I don't think it's going to be hard for you to graph the lines. You probably might forget to scale your axes, but I don't know. Just know if you're dealing with big numbers, you're going to have to scale it. You know, if they're little numbers like 1, 2, and 3, and that's one thing. But when they're bigger numbers, you have to scale it. Go by 10s, go by 5s. And then, you know, substituting into the objective function I don't think is difficult. And then make sure that you answer the question fully and completely. Okay, well, if you have any questions, please post on the homework discussion or ask in class. Your homework is on page 142, problems number 5 and 6. There's only 2 problems. So again, if you have questions, please let me know. Remember, I can't help you if I don't know you need help. Have a great day.